Hi everyone, my name is Besmira Nushi, and together with my colleagues Amit, Sharma and Mehrnoosh Sameki, we are going to guide you through an introduction and demonstration of the Responsible AI Toolbox. The Responsible AI Toolbox is our latest release on machine learning tooling for accelerating responsible AI, and it integrates together several mature tools in this space. Our agenda for today will be as follows. First, we will give an introduction to the release. Then we will follow up by showing how the toolbox can be used for debugging machine learning models, for counterfactual analysis, and then we'll jump to a demo on the causal decision-making capabilities of the toolbox. Finally, since this is an open source offering, we will wrap up by identifying potential collaboration paths within the toolbox as a research platform. Before we start, I'd like to thank our team that is distributed across several Microsoft locations and groups in Microsoft Research and Azure Machine Learning. The toolbox wouldn't be possible without the research contributions of Microsoft Research in Redmond, New England, India, and New York, and the contributions of the ITER committee and the great engineering and design work that was led by Azure Machine Learning and the teams in Ethics and Society. So the Responsible AI Toolbox is an open source and interoperable framework for accelerating the development of responsible AI. It integrates together several of the RAI tools that different Microsoft teams have built in the past in areas like interpretability, error analysis, fairness, data exploration, and causal decision-making. Even though many of these areas traditionally have been studied separately, in practice they are not independent of each other, and machine learning practitioners may need several of these functionalities to fully identify, diagnose, and mitigate issues, and also to take actions in the real world. To provide end-to-end fluid experiences, the RAI Toolbox allows you to customize your own analytical processes in a modular way, and it considers each of these pieces on data exploration, interpretability, as building blocks for the workflow. We will see together that the workflows are highly interactive, but they can also be used together with machine learning code in Python. So instead of considering these aspects as independent components, which may lead to experience fragmentation, it is now possible to build all workflows with very different Lego pieces, and you can adjust that workflow according to the domain or the problem that you are investigating. There are two main types of responsible AI workflows, either for the purpose of debugging machine learning models or for causal decision-making to take actions in the real world. Debugging workflows offer capabilities around error identification, diagnosis, and mitigation. For example, you might have initially built a model, you want to understand how the errors are distributed, then you may want to diagnose the errors either through data exploration or explanations or counterfactuals, and based on these insights, then you may want to take an action to mitigate them. The causal decision-making workflows instead often start with just interactive data exploration, and then we are integrating brand new capabilities on causal inference by leveraging well-known libraries on counterfactual generation and also by using the EconomL and DoWhy libraries. So without further ado, let me guide you through the machine learning debugging scenarios using the Responsible AI Toolbox. In this demo, we are going to debug together a machine learning model that was trained by using the UCI income dataset. The task of the model in this case is to predict whether an individual is earning more or less than $50,000 a year by using features such as education, work class, age, and so on and so forth. Here we are training a model using 5 estimators in the ensemble for a LightGBM classifier. And then we are giving this model as an input to the dashboard along with the training data and the test data. Then it's also possible to configure the dashboard by using different components. In this particular case, I'm using an explainer component, counterfactuals, and error analysis. So let's see how the dashboard surfaces this information to the data scientist practitioner. Here we see that the first component in the workflow is focused on error identification, and we're using this from error analysis. We can see that the overall error rate for the test data set is 19%. However, through this tree visualization, we can also see that the error rate dramatically increases for individuals who are married. They have a high number of education years, but a lower capital gain. And so, since this seems to be problematic, then I'm going to save these cohorts for later use. For example, I'm going to save this one on married individuals, and also this one on married individuals that have a low capital gain and high education. Yet another action that I can take on error identification is to slice the errors based on perhaps sensitive features and attributes that I'm interested in. For example, I can look at how errors are distributed across gender and number of education years. And I can see that as the number of education years increases, the performance of the model becomes worse. And in fact, this seems to be more problematic for male individuals rather than female. Having all this information presented, then next I may want to understand better what types of errors the model is making in these different cohorts and in overall. And I can go to the next component, and I can see that in fact, for the two cohorts that I created earlier, the ratio of the number of the false negatives seems to be higher. So there is a lot more false negatives here, meaning that the model in this case is underestimating the income of these individuals. So this is yet another information, and now I may want to continue the diagnosis process, and I may want to understand the data distribution better and try to understand if perhaps there is some sort of class imbalance in the data. So now I'm going to the Data Explorer, trying to understand the distribution. And I can see that, in fact, for the whole data, there is an obvious imbalance. There are more individuals earning less than 50K. And when I go and look at the distribution for the other cohorts, I can see that this imbalance now goes into the opposite direction. And this may explain the fact that there are more false negatives and the drop in accuracy in this particular data, which gives me insights in case I want to augment the data in the future. Perhaps I should focus on augmenting or adjusting to this data distribution better. Next, again, in the diagnosis process, what I can do is to go and look at the most important factors that the model is using in order to take these predictions overall. And I can compare them across different cohorts. For example, here I can see that the marital status and number of education years seem to be important in overall. I can also look at the direction through which this importance flows. For example, I can see that the lower the number of education years, the more likely this individual is to earn less than 50K. As you can see, the whole end-to-end workflow exposes the user to different angles of the data and the model story. And also it's possible to customize this workflow according to the problem. For example, I can easily remove one of the components here, or if I'm interested, for instance, to look at the raw data here, I can add another component in between in the workflow in order to look at the raw data. For example, if I click around here, then here I'm going to see the data in this cohort. I can generate particular local explanations for these records and try to compare them with each other and perform instance level debugging. Now, instance level debugging can be even more powerful through the generation of what-if counterfactuals. And Amit Sharma next is going to explain you how that works and how it can be useful for your debugging processes.
Thank you, Besmira. I'm Amit Sharma, and I'll talk about how instance level debugging and explanation can be done using what-if counterfactuals. What-if counterfactuals allow us to perturb features and observe how the model's prediction changes. So this is a very common requirement when we are analyzing machine learning models. We want to know if I change this feature, how would the model react? In addition, what this tool allows you to do is to do it automatically. So you could say, I have a point, I want to know what features to change its prediction, right? And this necessary feature that may be useful for you to understand what is the kind of input that is driving the model's prediction. Let me explain it using an example. So imagine you have a point here, which actually has a prediction of less than 50K, right? And this visualization actually allows you to look at many different points. But now let's just focus on this one, right? You may ask the question, what features need to change such that the model's prediction now changes and the person is now predicted to be richer? So the first thing that we can see using this tool is an overall summary of what features the model thinks are important here. Of course, the first one that comes up is capital gain. No surprises there. You have more capital gain means your income will also increase. But the second one is a cause of concern. It's also saying that in sometimes changing marital status, perhaps in combination with capital gain, may also help you with your income. Now, of course, this could raise fairness concerns, but also be a problematic feature if it's capturing some kind of correlation. So to drill deeper, we can now look at the individual data points, right? So now we are literally looking at a data point which is given here as the first row, and then asking the what if simulation, right? So here you can see, for example, if you have the same person, but with only two features changed, their capital gain increases and their marital status changes, then they would be classified as richer. But interestingly, that's not required. Even if you just have a capital gain, but a slightly higher capital gain, you would still be predicted as positive. So this analysis already helps you understand what kind of changes the predictive model is looking at, and it can help you understand also better what kinds of bugs your model might have. One of the benefits is that now you can start thinking about what are the other features that might be important, right? So this tool allows you to say what features should be kept constant and what features can then be changed to allow more insight. To save us some time, I've pre-computed one such analysis. So suppose you thought that capital gains is obvious, right? Let me just remove that. So now you ask a different what if question. You ask, what if the capital gain remains the same, but now I want to see if other features can tilt the balance and still make this person predicted to be rich, right? So here's an example. Let's take a different person now. This person also has been predicted as low income. And what you see now is capital loss becomes the most important feature. Again, no surprises, but let's drill down and see what we learn from the actual counterfactuals. Wow, here's something surprising. As you can see, the original person had a capital loss of 0, and this model is saying that if you increase the capital loss, so for example, the example 3 shows that if you increase the capital loss to 3,000, then the model will predict that the income should be higher. Now that's nonsense, right? You would all agree loss is bad. But I think what's happening really is that the model has captured some correlation. Perhaps only the rich people tend to have capital losses, and that's being captured here. And so you can see how this simple tool, this simple what if analysis, has helped you capture different kinds of errors and explain your model. This functionality is powered by an open source toolkit called DICE, which generates diverse counterfactual explanations for any machine learning model. And it helps us achieve twin objectives of both explaining a model as well as debugging a model. As I showed you, we have the option of including user constraints, which helps you customize the generated counterfactuals. And you can choose from a bunch of state-of-the-art methods for generating your counterfactuals. With that, I want to say that while DICE supports what-if simulations, it is still reflective of the correlations that the model has learned. For decision making, we need something more. We need to understand the causal relationships between features and outcome, which Mehrnoosh will describe next.
Thank you very much, Amit. You set the context quite well. As you saw, the previous parts was showcasing how different capabilities like model interpretability, error analysis, what-if analysis, data exploration, and counterfactual example analysis were coming together to help you analyze, validate, and assess and understand your models better. But also, sometimes you want to take informed decision. So the next piece is talking about how we incorporated causal inferencing in this toolbox for you to take informed and data-driven decisions and understand the causal impact of treatments on real-world outcomes. So let's look at a demo together. So let's look at a demo on the apartments dataset where the outcome is the actual price of an apartment. And there are features like number of fireplaces, garage cars, basement, full bath, etc., which are supposed to be helpful in terms of identifying how that particular house should be priced. And so your goal in this case is to understand how changing these treatments, say number of garages, number of fireplaces, would impact the real world housing price. And so in this data set, in this example, I'm just enabling the causal. I'm not passing any model. There is no machine learning model here. And I pass the model analysis object that is loaded with causal insights to my model analysis dashboard. Let's look at the widget together. Upon loading this dashboard, you're going to see 3 different tabs: aggregate causal effect, individual causal what if, and treatment policy. The very first one is hoping to answer what if questions about this real world outcome, in this case housing price, and how that would have been changed under different treatments and different policy choices. For instance, it can tell you that increasing the number of garage cars by 1 unit will increase the overall housing price by 20K, or increasing the number of fireplaces by 1 unit will, in average, increase the housing price by 8K. While this is an overall understanding of the impact of that particular treatment on the price, this is here to help you understand an personalized intervention and an individual intervention. So how about this particular house? What's going to happen to this house if I perturb any of its features in the real world? How the housing price will be impacted? And finally, there's a treatment policy that helps you build policies for future intervention. You can kind of identify what parts of your sample experience has the largest response to the change in the causal effect, causal features, or treatments. And so if I want to explain it on this example, imagine you wonder for what houses you need to expand or create or make a screen porch, and for what houses it's better to remove it. And so this is your customized intervention policy for you. For houses with overall condition less than this value and a small lot, the recommendation is to decrease, so expand, create, screen porch, versus if the lot frontage is small and the overall condition is low, then the recommendation is to remove or decrease. And so that might make sense in that sense that if the lot is quite big, then it makes sense to increase and create a screen porch. But if you already have a small and old house or lot, then the recommendation is not to expand it, but also remove it. And similarly, on the second row of this table, you would see that if the floor footage or the square footage of the house in the main level is less than a value, even if the condition is good, the recommendation is to decrease or remove the screen porch, versus when the actual square footage of the main floor is big or larger this value and the house has a good condition, then the recommendation is to add the screen porch. So that is helping you to understand that, oh, if I just go by the default of I need to create screen porch for all the house, that's how much an average gain you will see in the real world housing price boost. And if you go with this recommended policy that you saw in this table, as you can see that the housing price will be boosted even more. And one final thing to notice is there is a table here which has been sorted based on the effect of recommendation. And so I'm now seeing the first 10 houses which has the largest response to either removing or adding a porch. And so if you have limited and finite resources, you can only go with the houses that are more receptive to that particular treatment feature. And one thing to bear in mind is, of course, adding or removing a screen porch in this dataset has an expense, has a fee or cost. And so this also helps you kind of balance that. What is that impact that you're going to see by spending that money versus the effect that you hope to see based on this causal analysis on the real housing price, and truly choose whether that is worth it for you. The functionality that I represented in this demo is backed by an open source package called Economist. Really recommend you to check that out. It's a Python package that applies the power of machine learning to estimate individual causal responses. So to summarize, this is a toolkit that brings together all of our previously released capabilities under one roof, hoping to help you assess, understand, and evaluate your models, and also make informed data-driven decisions. We chose to build it in the open source because we always love and welcome community collaborations. So we truly see that as a platform where you can come and plug in your own research and modules and visualizations and sample notebooks. So please join us to co-create the next stage of this toolkit, expand it together, and also we always welcome GitHub issues and feature requests from you. Thank you very much for your attention.